Hello and welcome back to our instructional series on the Mentor EM, eddy current instrument. In this installment we're going to talk about rotary inspection of bolt holes. Again, I'm Dan Groninger from GE Inspection Technologies, and thanks for joining us. So to do rotary bolt hole inspection, we have a series of probes that are closely aligned to the hole that we're going to inspect. In this case I have a simple aluminum field standard here with a 1/4 inch diameter hole drilled through it. There's a tiny little corner notch in the top surface, which is very difficult to see. Halfway through the top is a side drilled hole. The bottom of the standard is assembled from 2 pieces of plate so that there is essentially a crack the whole length of it on opposite sides of the diameter of the hole. So think about this being part of a, say if this aluminum was part of some critical assembly on an airframe and you were going to put a bolt or a rivet through that hole. If there were cracks in the side of the hole, stress over time could cause the cracks to radiate, grow, and lead to the failure of the part. And we don't like to see that. So what we do to inspect a hole like that is we have a probe and a little motor drive that can spin the probe. So the active area of this probe is a tiny black dot, about a 1/16 of an inch in diameter down here on the tip on the outer diameter of that probe. So we spin that probe at high speed as we pass it along the hole, and we essentially inspect a helix through the hole. Now we have added some special features to the Mentor EM to control the speed of the drive and to start and stop the scan very easily with the button on the drive unit. So we have the drive unit comes with its own cable. That plugs into input 1 of the Mentor, and we use the Rotary mode app. So as we launch the Rotary mode app, very simple layout. We have a time-based view on the left. We have a lissajou or impedance plane view on the right. We have a control at the top of the screen to adjust the rotational speed of the drive. On the strip chart, we're going to reduce the buffer time, the scan time, a little bit. We tend to collect a tremendous amount of data in rotary mode, so shorter scan buffers are a little easier to deal with here. And the strip chart is going to work differently in rotary mode. And the instrument will automatically detect that you have a rotary drive plugged in. It will change the behavior of the strip chart or the time-based view to show you exactly one rotation at a time, or some number of rotations that you get to choose at a time on the strip chart. So there's an index detection inside the probe, inside the drive, and it will detect when the red dot here on the probe is aligned with the cable, and it will put that at the center of the screen. And as the probe makes exactly one rotation will go from the left side of the display to the right side of the display on the time base. All right, so you're always looking at exactly one rotation, or again, you can select 2, 3, 4, 5 rotations, but you'll see one or a couple of rotations on the time view, and the same one rotation or so on the lissajou. And right now we have no data flowing because the probe isn't spinning. If I push the black button on the probe, it begins to spin. You see I have data now appearing. I've got a green dot in the center of the display. I've got a flat line on the time-based view in green. If I do a balance, now if I take my probe and I start it into the hole in the block, there the probe is just starting to detect the corner notch at the very edge of the hole. Okay. If I go a little bit deeper in, there is the side drilled hole. As I go to the back side of the plate, now you see I have 2 indications. I'm seeing one revolution of the probe on a time base on the left, but I've got two big indications there. And that's because the way this plate is made, I've got essentially a crack on two opposite sides of the hole. So the crack, right now, the way I'm holding this, my corner notch is directly in line with the cable coming out of the probe, so it's pretty well centered on the screen. Side drilled holes in the same place. The double crack is at 90 degrees out from the side drilled hole. Right? So let's start the probe all the way at the back of the hole. We'll bring it out through. There's the double, side drilled, corner notch. I'm going to freeze. Okay. So if I now go to overview mode on time base, I waited too long. So let's do this. We'll clear. Started spinning. Go deep. Come back out. Press the button on the probe, and I freeze. You notice when I turn the rotation of the probe off, the instrument automatically goes into freeze mode. So now if I come here to my time base, hit the overview. Now what I see in the overview is every rotation for the last couple of seconds. So my gestures work a little bit differently in rotary mode than they did in surface mode. Now if I put my finger down and I place a cursor, the cursor will just follow the movement of my finger. And the cursor will always stay exactly one rotation wide, and whatever I select with the cursor is one rotation of the probe. So I see the indication on the Lissajous, and I see the indication on the time base that goes with the rotation of the probe that's underneath the cursor. So if I put my cursor over here, there's my two cracks in the back half of this standard. If I put my cursor here, there's my side drilled hole. If I put my cursor here, there's my corner notch. And now all of my other gestures that I'm accustomed to, you know, the pinch or the rotate, the pinch, those all work on these views as well. You notice I recalculated when I changed to phase angle, when I changed to gain, it recalculated the entire buffer in time. Because this is spinning at a high speed, we're using a very high sample rate here. Normal surface inspection, you might run 1,000 hertz sample rate. You're taking 1,000 samples per second. Here we run 20,000 samples per second. Again, because the probe itself, the probe element, the coil is so tiny and it's rotating at such high speed, we use a much higher sample rate. Another feature of the rotary inspection is that we tend to use filtering quite heavily. If we turn the filtering off, that's the kind of indication that you're getting from your signal. So it can be a little bit difficult to interpret. When the filters are set properly, the high pass and low pass cutoffs for the filter, you'll get an indication that looks very much like this from a notch. You'll get two little descending sacks underneath and one ascending indication from the notch itself. If you look at the filter response on a time-based view, these bottom two legs of this response you want to be of roughly equal height, and the indication in the center tells you something about the size of the notch. So we can come in here and we can change our filtering, and you notice as we adjust the cutoff frequencies of the filters, everything recalculates, redraws, and we begin to lose the shape that we were looking for. So if we come back in here and we make subtle adjustments to our filters, we can get those two legs roughly equal. At any point, if we're happy with our setup, close our menu, we press the button again, probe begins to spin, and we can make adjustments. Okay. While the probe is spinning, you notice when I have the probe frozen, I can't adjust my speed. Start the probe spinning. I can slow the probe down, and I'll put this over here. You might be able to hear the okay. So you can hear the change in speed of the drive. Speed of the drive is closely related to your filter settings, so be careful of that. But that gives you a basic demonstration of rotary bolt hole inspection with Mentor EM. Again, I'm Dan Groninger for GE Inspection Technologies. Thank you for joining us.